Everyone, what we're looking at today is this idea of where voltage or electric potential stays the same around different charged objects. What we can say is that if you're at the same distance away from a point charge, the electric field is the same everywhere at the same r distance away. So if I move from location A to B, like in the picture here, I'd be moving perpendicular to the field, so my energy would not be changing, which means my voltage would not be changing. So I'd have the same voltage from point A to point B. So let's calculate the voltages at different locations away from a charged source and see what we can do to find out where these regions are that have these equal potential surfaces. So what I've got here is a 6 nanocoulomb charge sitting at the origin there. You can see the electric field is pointing away in all directions because it's positive, and I can bring a little test charge in there and show you that wherever I put that charge around that point, the electric field is always pointing radially away. Let's do this. I want to know where around a 6 nanocoulomb charge we can get voltages of 500 volts, 400 volts, 300 volts, 200 volts, even 100 volts. In order to solve for that, since it's a point charge, I know my list of volts that I want to investigate from 500 down to 100. Charge is a 6 nanocoulomb charge, and I'm going to use K instead of 8.99. I'm going to use it as just 9 10 to the 9th. So that'll make my math a little bit easier. My question is, what radiuses do we need? What R values will give me all of these voltages away from my point charge? You've got the variables that you need, put them in and solve. So here's your answers there. If you want to find out locations where you're at 500 volts, 400, 300, all the way to 100, I just rearranged my formula, solve for R, and I got these distances. So 500 volts is about 10 centimeters away from the 6 nanocoulomb charge. 400 volts is 13 centimeters away. 300 is 18 centimeters. Then it starts getting big at 0.27 and 0.54 meters away. We're going to use the simulator here to actually plot out all those locations of equal volt. And like we said with this test charge here, if I keep this test charge at the same distance, you can see that the electric field strength looks the same whether I'm on the right side or the left side. If the electric field strength is the same, then I've done no work to walk from one side to the other as long as I keep the same distance away. And if I am not changing my amount of potential energy, I'm also not changing my voltage. So we have a voltage meter here, and I'm going to put it 10 centimeters away from the charge to get my 500 volt range. I want to draw my 400 volt range, which is only a few centimeters off. Then I'm going to go with my 300 volt range, 200, and finally 100. Could try to go to 0, but you can see that way out here at infinity is where I'd have 0 volts from this positive charge. And the simulator does a nice job of showing us where the voltage is most intense. It's most intense around the positive charge. And you can see that they've shaded it very red around those locations. But if you look at this, you're seeing these concentric circles or these concentric rings going away from the positive charge. So even if I wanted to find the 50 volt range, I could put it in and solve. And the 50 volt range is a lot further away than the 100 volt. It's not twice as far away, it's even larger. And the reason for that is because of this 1 over R relationship. You can see that the electric field points away from the source, but the locations where there's equal voltage or equal potential are at the same distance around the point charge. How is that any different than what we looked at yesterday with our visualization of voltage? We said a positive charge was like a very, very tall positive mountain, a very, very steep peak, and you can see it flattens out as we get near the end. Well, what I have on here now is not the electric field lines, but the locations of equal potentials, or we call those equipotential surfaces. So anywhere you ride along this line now, you are at the same distance from the point charge, so you are not increasing your potential energy or decreasing your potential energy. You're keeping yourself at the same level. What that helps us do is actually visualize what's going on and where there's high and low energy. So what we're visualizing around these point charges are these locations where you're kind of at the same elevation up the mountain. So if I put this on flat view, you can see that the rings are very, very bunched together near the point charge because the voltage changes so dramatically when you're very, very close to that peak. But as you start spreading out further and further, you can see there's a bigger and bigger gaps between one potential level and the next. So for a point charge, you can drop very, very high potentials, or you can drop large voltages from the point charge out. But as you start to spread out, it takes a long time for you to stretch out your potential difference. Like what we did today in class, we built the mountains out of clay and we added water to look at where the water would touch the mountain to give us a new equal gravitational potential. And if we look straight down on top of that mountain, you would see concentric rings that were indicating where we were at different gravitational potentials. So the same thing's going to apply here with charges, and with charges you can see that we get the same type of thing. It's more like a topographic map. In a topographic map, each of these lines show me equal elevations for this location. So anywhere along this 8800 line shows me that the elevation is 8,800 feet above sea level. So as long as I follow that line, I'm going perpendicular to the gravitational field, which is down, and I'm walking straight across. That means my potential energy isn't increasing or decreasing. I'm keeping myself at the same gravitational potential. And where there's a big spread out between lines, that means there's a very, very low grade. Kind of like when we get to the edge of the point charge. There isn't a very large elevation. Where we get the lines bunched up really close to each other, the elevation changes very dramatically over a very, very small distance. So an equipotential surface is a location around charged objects where you get the same potential or voltage at each location. So for point charges, it makes nice circles, and for this bean shape, you can see that the equipotential surfaces kind of go out as larger and larger ovals. The nice thing about that is that the electric field is always perpendicular to an equipotential surface. You can see my potential surfaces here. I'll make another one out here at 20, and you can see no matter where we make a potential surface, the electric field is always 90 degrees to that surface. Whenever you cross equipotential surfaces and you go from high volts to low volts, you know that you're moving with the field. And if you move with the field, you know your potential energy is decreasing. If you go across the surface and increase your voltage as you head towards that charge, you know that as an increase in volts, you had to do work against the field and increase your potential energy. So equipotential surfaces are just a nice way to visualize how the fields and potentials look around charged sources, whether it's a plate, whether it's a point charge, or even the ring that we'll talk about a little bit later. So you've all seen images like this where you drive by and you see a bunch of birds sitting up on electrical wires, and you wonder, how in the world are they not being electrocuted? Well, just like we're talking with equipotential surfaces, charges want to naturally flow from high voltages down to low voltages. And when the bird puts both feet onto the wire, both feet are at the same potential. So the charges running through the wire have no motivation to run up one foot and across the other. So they really don't even move through the birds. So the birds are actually raised to the same voltage as the line. But the birds better be careful. They better not reach out their wings to a second wire. If they reach out their wings to a second wire, and that second wire is at a different potential, say that that bird is standing on a 5,000 volt line and the other volt line is at 6,000 volts. Well, charges from the 6,000 volt line will feel the need to go from high voltage to low voltage as quickly as possible, and if you're the path in between it, then it will zap you. Kind of like this bear. This bear climbed a telephone pole and he was fine up there while he was touching the wires. The unfortunate thing with him is that he was raised to that high voltage and accidentally kept touching the grounding wire. So charges went from the bear at the top all the way down to the ground, and he was the path. He was the connection from top to bottom. So you can watch that video and see why the bear received that gigantic shock by touching the high volts and the low volt line. But there's another group of people where it's their job to actually stand on power line. And if you actually fell out of a plane and had to catch on to something before you hit the ground and all you had were power lines, you'd actually be 100% safe as long as both hands were at the same potential. So holding onto that line, you'd be raised to the voltage of the line, you'd be raised to that potential, and as long as you didn't touch the ground while connected to the line, you'd be 100% safe. It's only when there's a chance that charges can flow from a high volt to a low volt. So if you reach out and touch the pole itself at the same time, so if that power line is at a 5,000 volt potential and you're just hanging on it, then you yourself are actually energized and raised to 5,000 volts, and you're perfectly safe. The problem would be is if you're hanging over here, raised to 5,000 volts, and you reach out and touch the grounding wire. Now there's a path to flow from high volts to low volts right through you, and charges will ground themselves if they have the chance to flow from high to low energy. So really, your safest bet when you're hanging on the wire is to really just let go. If you let yourself go, you will fall to the earth and you will become de-energized by the time you reach the surface. The only thing you have to worry about is accelerating and striking the ground at a large speed. But you'll be safe from electrocution because once you let go of the line, you'll return back to zero potential. So these guys that work on high voltage lines here, they don't climb up the poles and grab on the lines to fix them. They actually reach out with a Faraday suit, and you can see that the electricity raises the potential of the person and the helicopter. Since they're all metal, the person's wearing a Faraday suit and the helicopter's all metal. As soon as they are both raised to the same potential, he can touch the line, everything's good to go, and he can climb out onto that power line. Once he's on the line, he disconnects the cable from the helicopter, and you can see the helicopter flies away, the helicopter becomes de-energized without touching the ground, and the guy can walk on the line safely. He's raised up to whatever voltage that line is, but he's on an equal volt surface. If he reached out and touched the line across from him, where that other guy's working, then he'd have some problems. Or if he got to the very end and touched a grounding wire at that edge of that pole, then there would be a path from high to low volts. But you're perfectly fine to crawl on electrical wires if you're in a Faraday cage.